Welcome to Brain Vision.
Okay, so here we're dealing with audible wavelengths. It says the range of audible frequencies, so frequencies you can hear, is about 20 hertz to 20,000 hertz. It's a pretty large range if you ask me. And we want to know what the range of wavelengths is from of audible sound in air. So range of lambda. So we can just here go ahead and use our handy relation. V is equal to lambda f, which holds for pretty much all traveling waves that we're going to deal with. And go ahead and plug in the speed of sound in air here. V is equal to 344 meters per second. So for f is equal to 20,000 hertz, lambda is going to be V over f, which is equal to 344 meters per second over 20,000 hertz. Remember, hertz is just 1 divided by second, which is about 1.7 centimeters. So that means the distance, the wavelength of a sound wave here in air at the highest frequency you hear is 1.7 centimeters. So you can visualize that kind of between your hands. It's kind of cool. So for f is equal to 20 hertz, we get lambda is equal to V over f, which is 344 meters per second by 20 hertz is equal to 1.17 meters, which means that the wavelength for the lowest sound that you can hear is huge. That's 17 meters. That's a sizable amount. That's over 45 feet, you know. So yeah, it just shows that the range of human hearing corresponds to a very large range of wavelengths. And that's all for that problem. Oh, that's all for part A, rather. So we can go to part B now and discuss. So now we're moving on to visible light. It says the range of visible from 380 nanometers. So I'll just write here, visible light. So all the light you can see ranges from lambda is equal to 380 nanometers to, let's tidy this up a little bit, 750 nanometers. And we want to know what the range of frequencies is. So we use our same old V is equal to lambda f formula to get that. Except here now, V is equal to the speed of light, which we reserve a special letter for, c. And that's approximately 3 times 10 to the 8th meters per second. Very, very fast. In fact, the fastest you could possibly go. So f is c over lambda. Let's start here with, how's about 750 nanometers? So for 750, that's going to be 3 times 10 to the 8th meters per second. And now nano corresponds to 10 to the minus 9, if you don't know that. You might want to commit that to memory if you don't. 10 to the 9 minus 9 meters. Oops, I'm sorry. Should be 750 here. Which is equal to 4 times 10 to the 14 hertz. That is a massive number. That means the frequency of visible light is incredibly high, which makes sense because it corresponds to an incredibly small wavelength, and there's an inverse relationship between wavelength and frequency. So for 380 nanometers, we do the same thing. F is equal to c over lambda, which is 3 times 10 to the 8th meters per second, divided by 380 times 10 to the minus 9 meters, which is about 7.89 times 10 to the 14 hertz. So I hope you see here that as wavelength goes down, frequency goes up, and vice versa. As long as we're at a constant speed, which we are because we are dealing with just light here, so it's the same speed, provided that we're not changing media. So now, new subject, brain surgery. So it says surgeons can remove brain tumors by using a Cavitron ultrasonic surgical aspirator, which produces sound waves of a frequency of 23 kilohertz. So we have sound, which is at 23 kilohertz, so that's the same as 23,000 hertz. We want to know what the wavelengths are of this sound in air. So we just use our same v equals lambda f, but now we're moving back to sound. So the trick here with these problems is, what is my medium? What is the speed of the wave in my medium? And here it's 344 meters per second. So if we take lambda is equal to v over f, then we get 344 meters per second divided by 23,000 hertz. And we get 1.5 centimeters is going to be that wavelength. Part D asks, now what if instead we had the same situation as part C, except our V is now the speed of sound in our body fluids. And it turns out that the speed of sound depends on the medium it's traveling through. So in air, it's one thing, but in fluids, it's going to be another thing. So apparently in our body fluids, it's going to be about 1,480 meters per second. And so if we want to see what the difference in lambda is, it's going to be 1,480 meters per second divided by 23,000 hertz. And what we're going to get is 6.4 centimeters. So takeaways from this problem are, make sure you know what medium you're talking in to get the right V, and observe that frequency and wavelength have an inverse relationship. All right, that's the end of that problem.